Good morning, and thank you for coming. I want to note that our speaker drove all the way from Tallahassee for this talk. So thank you very much, Dr. Sidhu. He is a regional specialized agent in agricultural water management. And in that position, Dr. Sidhu's interest is in optimizing water and fertilizer use in agricultural production. That is, to maximize agricultural yield while conserving irrigation water and minimizing necessary fertilizer application. You may recall that earlier lecturers in this series on Florida's Way of Water mentioned regulatory best management practices in agriculture, especially as one way to protect water resources from fertilizer nutrients and consequent aquifer nitrate contamination, surface water algal blooms, and other problems. In his position with the UF Institute for Food and Agricultural Sciences, Dr. Sidhu works with farmers, dairies, and ranchers in the Swanee River watershed to improve farming practices. A major part of that practice is irrigation management adequate for crop growth while protecting surface and groundwater resources, and at the same time meeting regulatory requirements and shifts in the global market for food products. Dr. Sidhu took his PhD in crop and soil sciences from the University of Georgia, master's and undergraduate degrees from the Punjab Agricultural University in India. At UF, he is a member of the Center for Land Use Efficiency, an affiliate of the Water Institute, and a graduate faculty in the agronomy department. He has numerous professional publications. Dr. Sidhu, please. Thank you.
Thank you, Phyllis, for the introduction, and I'm glad that I'm here, and I'm very happy to be here. So it really didn't matter to me to drive from Tallahassee, because I drive from Tallahassee every day to Live Oak. That's where I work. So so I'm habitual. All right. So when I got in touch with Phyllis, and she gave me the topic and asked me if I need to change the topic, and I said no, it's fine. But what I thought was that I will have my talk around the use of water in agriculture. So and the critical issues that we are facing, when it comes to the water use in agriculture. And there are two main issues that I will talk. First is water resource, and the second one is water quality. Now, what's happening in Florida, as you all might be aware of, is that there's a population flux coming into Florida, and this is one of the predictions that now in 2010 we had about 18 million people in Florida, which are supposed to grow to about 34 million people. The red zones that you see in these two maps is the predicted land use where the population centers would be. So that's, I just wanted to bring it to everybody's attention that if we are doubling the amount of people living in Florida, we need to prioritize our water. Now, what happens is that we have 5 water management districts in the state of Florida, and they plan and they forecast the use of water, and they identify projects to ensure that we keep on using, we keep on having water resource, and for us and for our future needs. Now, what has come to attention and is a point of concern at this point is for the growers especially is the MFLs, which is minimum flows and levels for our streams and lakes and rivers. So, and we need MFLs to make sure that our fresh waters, river waters, lake waters, we have it in a clean state, so that we can enjoy our recreation, but also, we still have water available for agriculture. But if there are instances where our MFLs or the water levels drops from a river or a stream or a natural spring, that has implications on water permits that are, the water permits used for ag purposes for the farmlands that are very close by to these water bodies. So this is one of the issues. Now, what's happening with our water resource allocation? This is a model predicted by Florida Department of Environmental Protection. As you can see, this is what was the water use. It's 6,405 million gallons of water used per day in 2015, and the prediction in 2035 is about 1,000 million gallons per day more water. Now, on a percentage base, you see that the percentage base for agriculture, the water use is reducing, because on a percentage base for our public supply, there is a huge increase of water. And if you recall the first map that I showed with the influx of population, that's what's happening. Now, having said that, the way water use will change varies from different water management districts. So if you look at some of the numbers here, so this is St. John's River Water Management District. So what will happen from 2010 onwards to 2035 is that the ag water consumption will reduce in and around Jacksonville area. Whereas for Suwannee River Water Management District, that's where my office is in Suwannee Valley, the ag water consumption is supposed to increase by 38%, because that's the hub, that's the heart of agriculture. Now, landscape and recreational water consumption, when we talk about water, we sometimes just focus on the ag water used on vegetables, row crops, but we tend to forget that we have lawns, we have backyards that need water, and we utilize significant amount of water over there. So what's happening is that due to the influx of population, again, in St. John's River Water Management District, there is supposed to be an increase of 45% water use, whereas in Suwannee River Water Management District, the increase is about 16%. So when we are talking about, or when we are trying to think about water use or future water consumption, we have to understand that the change will depend on where you are within the state of Florida. Now, the question is that we have this influx of people coming in, and we have an increase in ag production. Where will this water come from? So there are different ways, different projects. We'll be conserving more water. We'll talk about it. There are projects to use reclaimed water, to capture storm water, to use brackish water. So there are different projects where it's not my specialty, but specialty of other scientists that are working on those projects. But moving on from this part onwards, I will focus on my specialty, which is soil science, agriculture, and how we as soil scientists or agronomists are working towards, being more efficient in using water. And I'll talk about using water in agriculture. Now, and this is very basic slide, and I hope that all of you are aware of it, but I still had it in my presentation because this is very basic. This is how our soil holds water. So when we look at our soil, or some people just call it dirt, when we look at our soil, it has pores in it. And those pores have air and water. So when we irrigate more, these pores are filled with water. And then when we grow plants, the roots uptake water, water goes into the plant, the pores get filled with air. That's the air which has oxygen. That's where the roots get their oxygen from. And that's how, that's how the plants grow, or the water is retained in the soil. But what's important is the type of soil that we have. If we have clay soil, the water holding capacity in a clay soil is more because the pores are small. Water does not flow down with gravity faster. But when we have sandy soils, which we have here in north central part of Florida, any amount of water that we apply on a surface of water through irrigation or through rainfall, there's no water holding capacity because our soils are sandy. They have bigger aggregates, they have more spaces, so water just flows through those spaces. So that's one of the things very clear in this diagram. When we apply water on a sandy loam, what happens is that water straight away goes down. It doesn't go sideways because the channels are bigger. Due to the gravitational pull, water just goes down. Whereas on a clay loam, because the pores are small, water doesn't flow straight down. It tries to stay longer in the soil. Those soils have longer water holding capacities. The water goes in a sideways direction. Now, our soils are sandy. Our soils are even sandier than a sandy loam. So what happens is all the water that we apply in agriculture, we have to be very cautious of what we are applying, how much we are applying, where our plant roots are, because if we are applying more water, that infiltrates and then percolates below the root zone, that's gone. That's going down to the water table straight away because we have sandier soils. All right, so what we do, and this is some of the extension work, some of the demonstration work to educate our extension agents and educate our stakeholders, farmers, is we do a lot of blue dye tests to show them that when and how much we need to apply. And if we are applying more than needed, for example, you see here, this was after we simulated a leaching grain event, which was 2.5 inches of rainfall. And water went all the way to 33 inches deep. So that's below the root zone for most of the crops that we have. So these are the kind of things that we do at NFREC Swanee Valley, and you guys are more than welcome if you want to visit, if you want us to host you guys and show you around what kind of work we do. I'll be more than happy. Just get in touch with me. I can arrange a day for chauffeuring you around and showing you all the latest and greatest research that we do over there. All right, so what I also wanted to show was, if we do a blue dye test, it tells us a lot of things. It tells us where the soil was compacted, because where the soil was compact, water found ways to move around it and go deeper. But we also compared our blue dye test with the latest technology, that is soil moisture probes. And soil moisture probes give us a lot of information. For example, the top line here is the sensor that was placed at 2 inches depth. The bottommost line is the one where the sensor was placed at 34 inches of depth. And this soil moisture probe was placed right next to this blue dye dug up hole. So the first thing that you can notice was that is that this is the time when water started infiltrating down the soil profile, because the sensor right here bumped in soil moisture content. But it took water a few hours to bump the moisture probe that was 34 inches deep. So you can see here that water went all the way to 30, 33, 34 inches, but it took it a few hours. So soil moisture probes give us a lot of information, and that's what we are at this point dealing with. We are teaching our agents, we are teaching our growers how to use soil moisture probe, how to read the data from soil moisture probe, because most of the growers here in Swanee Valley, they are very adaptive. They have soil moisture probes, but the thing is that most of them don't understand how to read these lines. So, and I just have some of the slides to show you. This is how a soil moisture probe graph looks like. Sometimes it looks very intimidating, but it's not. It's actually very, very simple if we understand how to use it. When the moisture content goes down, it means your roots are active. They are pulling water from the soil. So your moisture in the soil is depleted. That's why you see a line coming down. This is nighttime. Sorry, this is night when the roots are not active. there's no decrease in your soil moisture content. Then the next day, again, there is a depletion in your soil moisture content, again, night. So that's your individual sensors on the top. The sensors might be placed conveniently where I want them to be based on what crop I am dealing with. For example, if I'm dealing with watermelons, most of my roots are in the top 1 foot. So I'll be concerned with the soil moisture sensors that I'm placing on the top 2, 6, 8, 10 inches. But if I'm dealing with corn, where I know that the roots go up to a meter depth, which is 3 feet, so I'll place my sensors strategically so that I get information of how water is being used throughout that profile. Now, this is an average or an aggregate. The lower graph is an aggregate of all the sensors that are placed on the top. So this line shows us is the uptake from the morning till the evening. The decrease in all the moisture content from different depths is the water uptake for that day. And now this was the water uptake for your next day. So the uptake could be different based on if the weather was cloudy, there was not enough heat, there was not enough sun, your crops are not growing that fast, your crops are not transpiring that fast, so your uptake would be lower. So it doesn't mean if I'm growing corn, so my uptake would be consistent every day, or it would be different. So I need to know how to read through these lines to understand how my crop is utilizing water. Now this one is very interesting. The first two, the blue, the graphs in the blue circles or ellipticals, the grower applied water twice a day. This is watermelon grower in Swanee Valley. He applied water twice a day for 3 days. And the next 3 days, he applied water 3 times a day. 1, 2, and 3. 1, 2, and 3. And this is what we told the grower to change from applying water 2 times a day to 3 times a day. And the reason when he was applying water 2 times a day, if you see these peaks, these are big peaks because he was applying a lot of water. Imagine, now try to come back to, we have sandier soils. You apply too much water, it's just going below the root zone, right? It's not being utilized by your plants. Me or a grower, from a grower's perspective, might be feeling very happy about, I applied a lot of water, right? But no, you applied a lot, but that's not being utilized by your plants. That's just gone below your root zone. So that's when we started reading these lines. We said, hey, you need to cut on twice, but start applying small doses of water, but 3 times a day. Now, what happened was when he was applying water twice a day, he was applying more water, but the actual water in the soil profile the actual water content was depleting because it was going below the root zone. Whereas when he started applying water thrice a day, we got a stable soil moisture content in our soils. So it's all about, when a new technology comes to us, it's our job at that point to figure out how to use that technology. And then it falls on us to teach our growers how to use that technology, because the technology is there. It's just the hesitancy from the growers, because looking at all that graphs, it sometimes is intimidating. But if there is a person who can explain the growers that this is how it is, once they understand, it's really easy for them to follow. So this is where our efforts go. A lot of efforts, even today, these soil moisture probes have been in place for a significant time, but even today, a lot of effort goes in explaining our growers how to use them. All right, so this slide is just a basic slide that how soil profile is. It has soil minerals in it, it has air and water. So our best job is to teach our farmers how to manage your water. So if we have too much water, if all the empty spaces filled with water, that's where the saturation is, right? And the field capacity is where when after saturation, when water is pulled down from the soil profile with gravitational forces, whatever is left is called field capacity. So the best way to manage water is to teach our growers to set up a management allowable depletion. That's between your field capacity and your wilting point. Your wilting point is the point where roots are not able to extract more water out of the profile because there's no more water that's available to the plants. So we have to set up a limit where the water from the field capacity depletes to MAD level, and that's when we ask our growers to irrigate so that they increase the water content and then follow the soil moisture probes. When the water goes down, they irrigate again, and so that they keep their moisture level between their field capacity and the management allowable depletion. Because if they grow their crops when the soil is too wet, when the soil is saturated, this is what's happening. At saturation, your roots don't get enough oxygen. Your plants will not grow because your plants need oxygen too. Because there's no when your soil is saturated with water, there's no oxygen. So your plants will not grow. They will look yellowish not due to nutrient deficiency, but due to lack of oxygen. And then if you are too close to field capacity right here, your plants will grow, but then you will still keep on losing more water with gravitational pull, right? So you as a farmer, or I as an educator, we need to educate our growers to be in this range. That's the best range to grow your crops and to save water, to be more efficient. All right, now, so that's what we do in terms of water resource and educating our growers how to best utilize the water resources that they have. And that can be through pivot irrigation, that can be through drip irrigation. There are so many things that we do, but that was the basic of what we are trying to teach our growers. Now, the other elephant in the room is water quality. And this is the biggest thing that we have right now. The biggest challenge that we have as UF-IFAS faculty is to manage nitrogen fertilizer up where we are here in the North Central Florida and manage phosphorus in South Florida. So I'll be talking more about nitrogen management and nitrate leaching because that's what my expertise is, and that's what I have been doing for the last 5-6 years since I moved to Florida. So this will be the second part of our presentation. And I just want to take a quick peek at my watch to see if I'm doing all right with time. All right, so what's happening with water quality? So there is a lot of pressure from state legislature to protect our waters. In 2016, Florida Springs and Aquifer Protection Act came in. And in Florida, we have 30 outstanding, out of 30 outstanding Florida springs, 24 of them have been identified as nitrogen impaired, which means that the nitrate concentration in those 24 outstanding Florida springs is higher than it should be. So most of you might know that nitrate, if it is higher than 10 ppm in concentration, it's lethal, it's toxic. So toxic not only to humans, but also to aquatic animals. So, and then if the nitrate concentrations are high, we can't use it for recreational purposes. So at that time, TMDLs were adopted. Let me use the laser. TMDL is the total maximum daily load, which means the concentration of a particular nutrient or element that should be in water, and the limits were set for TMDLs. And at the same time, basin management action plans were adopted. So for each water body that was vulnerable to water quality issues, BMAPs were adopted, and then growers within the BMAPs were asked to manage their nitrogen fertilizer or farm fertilizer in an efficient way. So what happened at that time was that Florida Department of Environmental Protection came up with their assessment of that how these different sources of nitrogen account for the total nitrate contamination in our Florida springs. And what came out to be was, for example, for Swanee River BMAP, farm fertilizer accounted for 60% of the nitrates. And for Santa Fe River BMAP, farm fertilizer accounted for 48%. So these are big chunk, big numbers. So now it came on to us as IFOS faculty to come up with efficient ways to utilize the fertilizer application. And then once we figure out the latest and the greatest technologies to be more efficient, the second part is to educate our growers and our extension agents so that, we foster a behavior change in our community to be more efficient. Now, in 2020, Senate Bill 712 came out, and after that, we have now implementation, verification, site visits. So what that means is that FDACs, their field reps would visit a farmer once in every 2 years to get all the records of fertilizers that have been applied on their farmland for the last 2 years. So then that gives them the ability to tally the crop that they grew and the fertilizer amount that they used. So this came out after Senate Bill 712. NARF is Nutrient Application Record Form that's used to put in all that information. There were other changes that came. For example, 20% of DEP's funds were to be allocated for nutrient management research, and I'll talk about some of the research projects in the following slides. And that bill also required FDACs and UF-IFAS to annually develop budgets to address agricultural runoff issues. All right, so these are some of the slides to kind of paint a picture of how much acreage falls under these BMAPs. For example, and I've taken an example of Swanee River BMAP. So it's divided into 3 sub-basins: Lower Swanee, Middle Swanee, and Withlacoochee. And so if you look at the Swanee River BMAP, there are a total of about 1.3 million acres in several of the counties in Swanee Valley. So it's a large acreage that's impacted by the BMAP. All right, so this, yes, ma'am. Yes, ma'am. Yeah. Yes, ma'am. All right, so these are the charts, and I just want you all to focus on this yellow color or mustard color on the screen. So for all these different spring sheds, Lower Swanee, Middle Swanee, and Withlacoochee, look at the farm fertilizer input in the based on the NSILT the software that Florida Department of Environmental Protection uses. So the nitrogen loading into our groundwater, the count of that from farm fertilizer is really high. It's 63% in Lower Swanee, 57% in Middle Swanee, and 76% in Withlacoochee. So what it tells is that we, as IFOS faculty and the growers, need to be more efficient. And for us, it tells us that we need to figure out ways to be more efficient on a scientific basis, to figure out ways. And then from extension standpoint, figure out practical ways, because science at sometimes science tells us white and black. Science can tell me that this is not the best way and that is the best way to do, but the best way that science is telling me sometimes it's not practically possible to be implemented on a 5,000 acre farm. So that's where extension plays a lot of role, or a big role for us to come up with practical approaches so that we can bring those scientific advances, maybe in a small baby steps, but bring those changes on a large scale level under the farms. All right, so this is, it looks like a busy slide, but I would like for you all to look at the 0.35 milligrams per liter. This is our target. For most of the BMAPs that we have in the state of Florida, the target to achieve in 20 years is as this, that we have this target in front of us now, that we have to reduce the nitrate loading to 0.35 ppm, and we have 20 years to do that. And it's not that from beginning of year one, we are expected to reach that number or reach the reduction number that we are looking for, but it's based on for the first 5 years, we are supposed to reduce or achieve 30% of reduction. And from 5 years to 10 years, we are supposed to reduce 50 more percent. And in the last 5 years, we are supposed to reduce another 20%. So it's a stepwise, incremental increase that we have to achieve in reduction of our nitrate loading in groundwater for us to be able to reach this number. Now, there has been many questions of how accurate is this number, or if we can actually ever achieve this number, because I'm part of a big multi-state grant led by Dr. Wendy Graham. She's the director of Water Institute at UF. And that project is a facets grant, and several of the modelers working together from Georgia, from Florida, they have looked into the Flint River Basin, and they have tried different scenarios. And some of the scenarios were that, what if we just take away ag and replace it by pine production and forestry? So there were several of these drastic scenarios that were checked or that were studied with the help of modelers, and it was very hard to actually achieve 0.35 ppm of nitrate even in 20 years. So I'm not sure if that number is that the ppm of nitrate in our spring waters is achievable or not, but the amount of nitrogen that has been tasked for us as IFAS faculty, that's the amount of nitrogen that should be reduced. I think that's possible. For example, in Swanee Valley, we are tasked with reducing nitrogen by 4.2 million pounds of nitrogen on a yearly basis. And I think that's achievable. And I'll try to convince you all that that's achievable in the next coming slides. All right, so this is ag land use in Swanee Valley. So the green dotted areas are fertilized lands, and the mustard yellow colors are the lands where we have livestock, dairies, and things like that. So again, where we have dairies, we have silage corn. So those are also farmlands which apply fertilizer. So this is what I was talking about, that this is our target in terms of pounds of nitrogen reduction per year. And for lower, middle Swanee, and then with Withlacoochee spring basins, if we add that total, it comes to about 4.1 million pounds of nitrogen to be reduced every year. So the reduction plan, as I said, is in a staggered way. So for the first 5 years, we are supposed to technically reduce application by 1.2 million, and then for 5 to 10 years, 2 million, from 10 to 15 years, another 815,000. That's how we are supposed to reach that target. Now, when we started thinking about it, that how we can reach, because when you look at that 4.1 million pounds of nitrogen reduction, it seems like a big number. It seems like you can never do that, right? But then when you sit and you start thinking about, like, okay, let's start doing some calculations and see if we can achieve that. So what we started talking about was that what are the primary users of nitrogen in Swanee Valley? Hay, corn, vegetable crops, and livestock waste. So we knew that the hay farmers, because the way they cut their hay multiple times a year and they need fertilizer multiple times a year. So at this point, we don't have that much of understanding that how we can manage hay production and nitrogen fertilizer application on hay. So that was not our first target. Our first target from being an agronomist, my first target was that, okay, let's focus on what we can do with corn, right? Corn is one of the crops that need a lot of nitrogen. So typically here in Swanee Valley and in Florida Panhandle, growers, apply close to 300 plus pounds of nitrogen to grow corn crop. So what we thought at that point was, what if we target corn and vegetable crops and see if we can reduce just 50 pounds of nitrogen per acre on a yearly basis. So for corn, we have about 50,000 acres in Swanee Valley. For vegetables, we have 20,000 acres. And if we are able to just reduce 50 pounds of nitrogen in corn and in vegetables, this is our number. We are pretty close to that. We are pretty close to 4 million pounds. We are already at 3.5 million pounds. So if we think that this is our target, improving our efficiency by 50 pounds of nitrogen, if we can reduce or convince our growers to reduce 50 pounds of nitrogen on an annual basis on their crops, we are pretty close to reach that. But I think we can do better. So this is a research work started way back before I joined in this position with one of the farmers in Madison County. So if you see these streaks, this is called banding of nitrogen. Banding of nitrogen means applying nitrogen right next to the plant row where the roots are, where the plant needs nitrogen. So this farmer alone grows 5,000 acres of corn and was able to reduce 50 pounds of nitrogen just by changing his nitrogen application method from broadcasting to banding, because now corn is grown here in Swanee Valley 30 inches apart on 30 inches apart rows. So if you are broadcasting fertilizer, and this is the point where I need the mic to go here so that I can show some hand gestures. So it's not working. All right. So if corn is grown on 30 inches apart and we are broadcasting fertilizer, which means if my hands are 30 inches apart, all the fertilizer dropped in the middle is not utilized because the roots are small. Imagine corn plant just coming out of the ground with tiny roots, and you're applying all the fertilizer in these 30-inch row spacings. It's not getting used, right? Now look at this picture. This is banding. It's applying nitrogen where the roots are. So that's very efficient. So this farmer alone reduced 250,000 pounds of nitrogen, which is about 6% of the BMAC target that we have. That was just one farm, right? So I'll try my best to build a case that we can reach there. So bear with me. All right. So, but to achieve that, we utilize some special equipments. This is a high clearance equipment. We call it a high boy. So I'm the PI of this project. This was funded by AFDAX and Water Management District. So, and DEP, but this equipment itself was funded by the Swanee River Water Management District. So this is, and I'll talk a little bit more about and show you all how we use this equipment in some of the slides that are coming, but this is a new project where we are demonstrating banding of liquid nitrogen in corn. So what we do is we select our farmers every year, 3-4 farmers, and if they are willing, multiple fields on their farm. What we do is we go out there and we apply nitrogen. It's their fertilizer, but we apply using this rig to show them, and this is the best way of educating a grower, is to show the grower on his farm what is the best way to do it. All right. Now, another good project that we have at this moment in Swanee Valley is CRF. It's controlled release fertilizer. So, what happens is that when we apply nitrogen as a conventional fertilizer, it's readily available. Now, if you apply nitrogen today and it rained, right? So even before the plants could have taken up all that nitrogen, it just went below the root zone. And I want you all to again think back. We have sandier soils, water doesn't stay, it just go down. So this technology, CRF, is a polymer coated fertilizer. So the polymer is basically the same fertilizer, it's just coated in a polymer. And that polymer, the dissolution of polymer in moisture is temperature dependent. So there are different companies that came up with different polymers, and we are testing those polymers. So it's temperature dependent. As we go from spring to summer, the temperature increases, the ability of polymer to release fertilizer increase, and that's when the crops are growing. So the point of CRF is slowly release fertilizer so that it's available to plant, not in one go. So even if you apply your CRF fertilizer today and it rains tomorrow, a heavy rain, it's not going to leach everything because the fertilizer is still in the polymer, because it is going to slowly release with temperature over a time period. So this is another efficient way of fertilizing. But whenever we are talking about new technologies, it comes with a cost. So I want to make a point here that most of these new technologies that we are testing at grower farms is supported by cost share programs. It's because the CRF fertilizer in itself is maybe about double the price of a conventional fertilizer, which in itself, the conventional fertilizer in itself is doubled from what it used to be in 2020. So it's an expensive product, but with the help of cost share from funding agencies, from water management districts, we have a project this year. It's a pilot project where we are demonstrating CRF on 7 watermelon farms and 3 corn farms. And that's fully funded by Water Management District and FDACs. So that's the technology part of the fertilizer. It is covered by these 2 entities. All right, now I want you all to come back to this slide again and see that with all the advances that we are making scientifically, if we can now think that if we can see that just in corn, not in vegetables, but just in corn, if we can be more efficient and reduce nitrogen from 50 pounds per acre to 65 pounds per acre, this is what our number looks like now. We are at 4.2 million pounds together for corn and vegetables. And we haven't even started talking about hay. We haven't even started talking about dairies, right? So I'm very optimistic because we are getting pretty close to that 65 pounds of reduction. Because as I told you, most of the growers in Swanee Valley, they apply nitrogen close to about 350 pounds, which we know with all the research and demonstration that we have done that we can grow decent corn with about 280 pounds of nitrogen. So that's the math, so we are not there yet. I'm not saying that we have reached this point, but I'm saying that we are pretty close to demonstrate and educate everybody that we can reduce 65 pounds of nitrogen and grow corn without hampering our yield. Now, I want you all to kind of zoom out a little because all those precision ag techniques using the high boy, using CRF, a controlled release fertilizer, placing the fertilizer right where the plant roots are, those are precision ag techniques. And you can only achieve, only achieve your efficiency to a point, and then you hit a plateau. All right. But if you zoom out and think about managing your farm from a cropping systems perspective, how you farm, how one farmer versus other farms, changing your practice. Just adding tillage, changing your tillage practice. For example, if a grower cultivates or turns his soil frequently after every crop, he's reducing his organic matter, which in turn reduces your water holding capacity, and things like that. Versus a grower who uses strip till, he does not disturb his soil, does not reduce the organic matter that's built up in the soil, which is very difficult to build up in Florida because of the heat and moisture that we have. But it still builds up, but at a very slow pace in Florida. But if a farmer adapts to better practices, his soil and his farm behaves in a better way. So now I have another project. This project is a 17-year funded project. And the first year of the project was infrastructure buildup, which is what you see on the screen, where we are comparing 4 different cropping systems. So the 2 cropping systems on this side are conventional cropping systems, which depict a normal cropping system in state of Florida and Swanee Valley, which is corn one year, peanut next year, corn one year, peanut next year, which is a typical farming practice. This quadrant shows corn in the summer, followed by carrots in the fall, followed by peanuts the next year. Now, in these 2 quadrants, we have added pasture, Bahia grass. So for first 2 years, we have Bahia grass, and then we follow the same our row crops, corn and peanut in one quadrant, corn followed by carrot, followed by peanut in another quadrant. Now, what we are trying to achieve with this project is to see the benefits of adding pasture land in your row crops. And this is not something new. This is not something that I came up with, or this is not anything new. It's how farming used to be several decades ago, when we didn't have cheap nitrogen fertilizers at hand. So every grower would have cattle. The land used to be rotated. We used to grow fodder, for cattle. The cattle used to graze the land, and then we'll move the grazed areas within our farm. That's how my dad did it. That's how I grew up on my farm. We had, acreage for fodder, and cattle used to graze those acreage, and every year that acres will move. So we all know that grazing of cattle and having pasture land has tremendous impact on organic matter, which has tremendous impact on water holding capacity and so forth. So we are testing this, and this is a great project, and we are learning the impacts of long-term impacts of different cropping systems on water quality. These are some of the pictures from that project. So we set up drain gauge lysimeters. These are drain gauge lysimeters. These are set up at 2.5 feet depth below the ground, so that in different cropping systems, when we apply fertilizer, we can track the movement of nitrates below the root, and that nitrates are captured right here at the bottom of the drain gauge. And then we vacuum the water, leach it out, and send it to lab. So we have been doing that for every week for the last 4 years, and intend to keep doing it every week for the next 12 years. And that will give us tremendous amount of data and understanding of how there are long-term impacts of, change in your cropping systems. So one thing, these are the pictures of my teammates collecting leachate samples that I just mentioned, that we are doing it every week. So one of the important things is that this year, starting from the 5th year onwards, we are adding another layer of cattle grazing on top of Bahia grass in this project, because cattle grazing has shown a tremendous improvement in soil properties and nutrient cycling, and also in the root properties of your following summer crops. All right, so I love this picture, and I got this picture from my former boss, Dr. David Wright, who I used to be a postdoc with him at NFREC Quincy. So this is what I was talking about. So these are deep soil profiles that we collected from different farms, and this is collected from a conventional farm. When I say conventional tillage, it's the farm that turns their soil after every crop to prepare their land. Do you see a dark color on the top? No, because there's no organic matter, or very minimal organic matter. Why? Because the soil is turned, and it's hot and humid, and organic matter breaks down and goes up as carbon dioxide. So no organic matter. So the middle profile was collected from a farm that changed its practice from conventional tillage to no-till and strip-till for 35 years. And then for the last 3 years, it was under Bahia grass. And see this dark zone right here? That's the buildup of organic matter in Florida soils, which typically we always, we always think that, oh, it's very difficult to build up organic matter in Florida because it's too hot. As I said, it takes time. It's a slow process, but we can build organic matter in Florida soils if we change our farm practices. Now, this was collected from a sod-based rotation, a farm that just implemented 2 years of Bahia grass pasture land in their row crops for the last 12 years, which means that land had three different cycles of Bahia grass in 12 years. So see how quickly organic matter started building up right here. So I just wanted to, for us all to think about that it's not only the precision ag techniques, it's not only the big machinery and the latest and greatest technologies. Sometimes it's just changing a small practice at our farm, which might end up having huge implications, not only on the overall management, but also on water quality. Now, I love this picture. This is peanut roots from a conventional plot where it was peanut cotton rotation. Peanut, cotton, cotton, peanut, cotton, cotton. That's a normal rotation in Panhandle, close to Jackson County. And these are the peanut roots from a sod-based rotation. The plots that were established for the last 20 years, where for the first 2 years you had Bahia grass, then your peanut, then your cotton. Bahia grass, peanut, cotton. Bahia grass, peanut, cotton. You see the change in the root. So what we saw is that you can improve your root biomass, your root structure length, your root surface area by double if you just put your land or rotate your land with a pasture, and then once you're done, you grow your row crops back into that pasture. But I wanted to, when I started working with Dr. David Wright, and I'm sorry, I wanted not to include any scientific data or graphs, not because I just didn't want you all to be bored by the graphs, but this is really important that I wanted to show. So the roots that you saw in the last picture was from sod-based rotation without any cattle grazing on top of it. When I joined Dr. David Wright as a postdoc, I said, let's try to see, what happens to the roots when we add cattle on top of pasture. So what we saw was that the root length increased, again, doubled. Root volume, again, almost doubled. Root surface area, again, almost doubled. So what I'm trying to tell here is you compare a farmer who is doing ag in a conventional way to a farmer who is having Bahia grass or a pasture land and has adapted to cattle grazing. There is a 4 times improvement in root length, root surface area, root volume. Now, guess what is happening? Sandier soils, water moving down, deeper roots, bushier roots, more volume, more surface area, all the nutrients which otherwise would have gone below the root zone into the groundwater now are being used by the plants, right? So I just wanted you all to kind of think about that just little changes in farm practices can have huge implications. And now I want you to think about the long-term project where I'm a PI. That's what we are trying to see. Long-term implications of all these things that I'm trying to share with you. All right, this is just a picture that I took from one of those plots which are established for the last 20 years in the same way. This is sod-based rotation cotton. This is Bahia grass, peanut, and cotton. And this is dryland cotton, never irrigated. It's dryland cotton. And the picture here is conventional cotton. And you see the conventional cotton is drooping. It's stressed out in the middle of the day. I worked with Dr. Wright for 4 years, looked at these plots every day, never saw this non-irrigated cotton wilt even once in 4 years. It's non-irrigated. It's just Why? Because of all that root structure improvement, so it has better roots, deeper roots, strong roots. It's collecting its water, but on the other hand, this crop doesn't have that kind of root structure, so it's drooping, right? So now imagine we have significant acreage in agriculture that is not under the pivots, that is non-irrigated. Just by changing your farm practice and your cropping system, you can have a better yielding crop, because your crops are not stressed out. So these are the things that I wanted to share with you all. All right, now this is really, I like this graph too. So what I have been talking with you all is the improvement on nutrient cycling by adding cattle grazing. So we wanted to see what's the implications, what happens deep, deep, deep below our ground after 20 years of making a change, right? So we used a geoprobe and we collected soil samples all the way to 8 meters of depth, which is close to about 24 feet. This white dot right here represents your conventional crop rotation without any Bahia grass. And the green dots represent grazing, and the purple grazing with irrigated lands. Now, what I want you all to focus is right here, right close to about 4 to 5 meters of depth, which is deep enough, which is about 12 feet deep, 12 to 15 feet deep. Look at the change in the nitrates that are deeper in the soil over 20-year period. That's a long-term impact on reducing the flow of nitrates deeper into your soil profile, which means low or less amount of nitrates are flowing down your profile, which means they are less liable to now enter. You have low amount of nitrates which will eventually enter your groundwater, right? Isn't that the point? Isn't that the target that we are trying to achieve, right? So this is what I really like this graph. So I'm a huge fan of cattle grazing on row crop land. I've seen that. I grew up on a farm. My dad used to do it, when I was young. So I understand the importance of cattle grazing, and I understand the importance of nutrient cycling when we add pasture and cattle grazing on our row crop land. So I've talked to several growers who have implemented these cattle grazing onto their row crop farms, and all of them agree that you cannot beat the system. This is a wonderful system. All right, so now I wanted to give a little bit of an update on the 4Rs project. Am I doing good with time? All right. So corn, as I was talking about, that we are targeting corn as one of our crops. So I quickly want you all to look at this area right here that I have marked. This is when corn is very small. It's 30 inches apart, planted, very small, tiny roots, right? So that's the first step where we can target and we can improve our efficiency. And that's what we are trying to do with banding, because we are trying to apply nitrogen where the roots are. Now, the second part, which I have highlighted right here at the very end, when corn now has a cob on the plant and it's in the reproductive phase, now all the nitrogen that's in the corn plant, in the leaf, in the stalk, and all the leaves, that has started to redirect to the reproductive part, which is our corn cob. Now, if you look at here, it's just taking a little bit of nitrogen from the soil, because most of that nitrogen is just redirection of nitrogen from different parts of the plant to the cob. So we thought of that this is the second phase in corn growth cycle where we can target and improve nitrogen use efficiency. And I'll show you all how we are trying to achieve that. So first of all, I wanted you all to see the banding application. This is the white knobs from the pipeline, and these are called white knobs. They look like an inverted cross. Holes from the top, and then two prongs at the bottom. And the two prongs are right where the plant row is. And this is how the liquid nitrogen is being applied with the high boy. right where the plant is, about 2 inches away from the plant, right where the roots are. Now, the question that you might have is, corn is too small. Why do we need a 7-foot tall highboy to apply? Yes, we don't at this stage. We don't. I needed to demonstrate to the growers. So, but if the growers buy into the methodology, if they buy into banding nitrogen, they can do liquid application or banding application of liquid fertilizer with a tractor pulled rig that they have, because corn is too small. They don't need a special equipment. But for us to demonstrate it throughout the season, we needed a highboy. So there are several growers who, after we collaborated with them, they come back to me and they say, Sudeep, do I need to buy a highboy? No. And I always say, no, you don't. If you have bought into the best practice, just do it with a retrofit your pull rig and put white drops on your pull rig and apply your nitrogen for the first 2 times when corn is small. What happens with corn plant is that when corn grows, it's like a funnel. You know, it's more broad on the top. So when you irrigate with a pivot, it has a funneling effect. All the water trickles down and falls closer to the plant itself. So you don't need to have a highboy at that growth stages. But when corn is small, that's when you need nitrogen to be placed where the plant is. All right, this is another cool video because some of the growers were very hesitant of using a highboy on corn because they thought of that it might bend the corn. Just took a video from inside the cabin. It doesn't bend the corn stalks at all. It's too high. No, well, that's a good question. Now you cannot ask me to drive this because I might ruin your corn, right? So we have a special guy who works with me. He's my teammate. He's the one who drives the highboy because yes, a little bit of a slide in your path and you'll run over the corn. So you have to have, even though it's a GPS guided, but still you need a specialized driver to take care of, you know, when you are in standing corn. Now, remember we talked about this later part of corn growth where we are trying to target nitrogen efficiency or improve nitrogen efficiency. So what we did is we retrofitted a seeder unit on the highboy. And as you can see, this is the seeder unit. This will hold seeds for a cover crop. And these are the hoses. And you can imagine the height of the highboy. This is one of my teammates. He's kind of my height. He's walking under that highboy. So you can understand, you know, this gives a better perspective of how tall the highboy is. So after we put a seeder unit in it, this is how the cover crop seeds were flowing out of the drop hose. Now what we are trying to achieve is, that's the corn behind this that you can see. It's not harvested. It is dry corn, not harvested. And we are trying to establish cover crops even before corn is ready to be harvested. Why? Because at that time, corn does not need nitrogen, but nitrogen is still in the soil. So we are planting cover crops so that the cover crops can start scavenging or taking up nitrogen, whatever nitrogen was left in the soil, even before we harvest corn. Why? Because that's the time of the year when we start getting rainfall every day. You have nitrogen sitting in there, we have sandier soils, and we have rainfall every day in the afternoon, right? So this is what we were trying to do. And one of the concerns of the growers was that now my corn is dry, highboy will bend my corn, and I won't be able to harvest it. So I said, okay, put it in the house. So this is what we tried in the Parishes County Valley to see if we are able to plant cover crops in standing corn before we harvest corn. So this is another one from the cabin. Nothing happened. We were able to plant cover crops, and we harvested corn a couple of days later. So now I have a PhD student whose whole project is to figure out what kind of cover crops we can plant in standing corn, how early we can plant those cover crops, 1 week early, 2 weeks early, 3 weeks early, and things like that. So there are several unanswered questions that I don't have answers to, but the PhD students working on to figure out that in the next coming years. All right, so this is the cover crop that we planted in standing corn. So this is a proof of concept that we were able to establish a good amount of cover crop on standing corn. Now, in this picture, this is the side where we applied where we planted cover crops in standing corn. This is the side where we harvested corn and then planted the cover crop. And you can see the difference in the height. Why? Because we saved about a couple of weeks here. It took us a couple of weeks to harvest corn, get the soil ready, then plant the cover crop. But there, we just planted it in standing corn. We had a blend of summer and winter cover crops. In the cover crop that we planted, it had a blend, and the reason we had a blend in that was so that we can reduce the number of passes. So we had summer crops and winter crops in it. So once we planted it, the summer crops came right away because it was still late August at that time. And then when we transitioned into fall and winter, the summer crops died, and the mustards that are the winter crops, so they came up. So it saved us time and effort and of course extra passes through the field. Now, grower hesitancy is there, when it comes to banding nitrogen, because, and I agree with the growers. See, that's what I was talking at the very beginning of my talk, that science can tell me black and white that that's the best thing. But sometimes practically it's not possible to use that best method on a farm. High boy. Now imagine a small grower, a 500-acre grower. High boy costs about $500,000. Is it worth for a 500-acre grower to spend $500,000 to buy a high boy? Probably not. Now think about big growers, 10,000-acre growers. They have 10,000 acres of corn. They can't even finish their one round with a high boy before they are ready for their next round of application, because most of the growers apply nitrogen 6 times or 7 times during the corn growing season. So it's a 10-day kind of a thing, weekly or 10-day kind of a thing. So they need multiple high boys, right? Whereas if they are applying fertilizer through their pivot, all they need to do is turn on their pivot and it fertilizes, right? So practicality versus science. So now, but we know that science works. We know that this can be done. If they are not able to buy a high boy, they can retrofit a pull rig and wide drop when corn is small. The first 2 or 3 applications are all that matters because the roots are small at that time. But there's another thought. If we think out of the box, this is what's happening right now. Your corn is planted and all these dots are corn plants, and forgive me, this is me being the artist that I am. So this is my best version of being an artist. So the red balls are the corn plants. These are planted 30 inches away. And when a water drop falls from the pivot, when we are fertigating, it falls and the roots are small. It's away from the roots, right? What if we change the placement? What if we plant corn closer to each other? The rows are 15 inch, and then we can adjust their spacing within the row, and make it more from a rectangular matrix to a more of a squarish matrix, so that if practicality is the issue and it's easier for the grower to still use the pivot so that they can keep using the pivot, but we change the planting matrix so that it's more efficient for, in terms of nitrogen use efficiency. So these are some of the things that are in our mind going forward. So I just wanted to share it with you all. Thank you. And I hope I didn't take much longer.
I've never been on a farm, but I can see what you're doing, and I think it's fantastic. It's a demonstration project for the whole state. And I wonder if other, of course, this is the land grant university here at the University of Florida, but I wonder to what extent your knowledge is being distributed across the agricultural producers of this state, like Duda Farms is huge. Are they learning from you?
Yes, ma'am, they are. And see, when there was last year we went to one of the farmers in Lafayette County, and after the end of the season, he came to me and his first question was, Sudeep, I like the idea, but do I need to buy a highboy? And I told him, no, you don't. You know, if you understand the proof of concept, and that's just apply nitrogen when corn is small, apply it close to the plant roots. You can just fit your regular pull rig with Y drops, and you can do it. So there are several farmers who understand once we go out on their farm and we compare. And for example, this year, I have 6 farms. I have 4 farms in Hamilton County. Well, technically 2 farmers, but each farmer allocated us 2 different farms. And what we are doing there is half of the pivot is what the farmer would do using a pivot, apply nitrogen using his pivot. Half of the pivot is what we will apply using the highboy. Now, and we keep the rates the same. Whatever the farmer decides that he wants to grow corn with, for example, 280 pounds of nitrogen, we keep the total amount of nitrogen applied using highboy the same. On the second farm, the farmer and I, we sat together, we discussed about the science, we discussed about that how efficient this methodology is, and we discussed and agreed upon a 15 to a 20% reduction. So the second field or the second pivot is where the farmer will apply his method and his rate, and we will apply nitrogen using the highboy, but at a 20% reduced rate, so that at the end of the season, I and my team can be able to show the grower that this is the difference in your yield when we applied the same rate of nitrogen using different techniques, or when we applied 20% less nitrogen by using highboy without decreasing the yield component. So yes, the farmers are learning, they are very interested. There are some hesitancies, and they are very logical hesitancies when it comes to purchasing an equipment such as a highboy, which is an expense. It's not a one-time expense because you have to have a specialized driver, and you need to run your equipment, and then there will be breakdowns of your equipment. So there are costs that are involved, but it's not about the highboy. It's about the proof of concept of banding nitrogen.
Questions?
Thank you for a very intelligent series of examples. I have a curious question, and it goes back to some early slides where you had the rainfall, the application of the water into various time periods in the soil. And I guess what I'm concerned about is you have stratified what we classify as stratification of the different districts within a land water management district. But I'm thinking of, if you go to a farm, how much variation in the soil would there be? In other words, you took one picture of a certain type of soil, but if you go to, let's say, a big farm, 600 acres or so, how many variations in the soil are there that you will have to sample to determine the results?
Very good question, and I guess I have a perfect answer for your question. So when I started working with Dr. David Wright in December 2017 is when I came from Nevada to start working with Dr. David Wright, and he started telling me about the sod-based rotation because he was the one who came up with sod-based rotation about 20 years ago, and he said, Sudeep, think about something to further improve this resilient system. And I said, Dr. Wright, it has to be variation, soil variation. If we can capture soil variation and then micromanage soil variation, the variability in the soil based on soil texture. So we have a various MSP3 unit, and I regret that I didn't add a picture of it, but it's an equipment. It's a tractor pulled equipment that has electrical coulters behind it, so it releases electrical current. So based on what kind of texture you have, if you have more silt, more clay, your conductivity is faster. Electrical conductivity is faster. If you have more sand, the conductivity is slow. So you run that various equipment onto a farm, it gives you a super high resolution map of your one field. Yes. And so what I did, I started working using the various, and that was my first step of precision agriculture onto Dr. Wright's already resilient system. And I'm just giving one example. This is out of a published paper. Dr. Wright had been preaching that if you have sod-based rotation, you can grow cotton, a 3-bale cotton with 60 pounds of nitrogen, which is fine, which is very good. When I added the layers of precision ag and divided the variability, and I came up with another technique, because now I know, for example, now I know that part of my field is better than this part, right? Now the next question is, okay, I know that's better, this is not that good, but how to apply nitrogen? How much nitrogen do I need to apply on a better part versus the other part? So I came up with a technique that's called calibration strip, nitrogen calibration strip. So based on the calibration strip, I was able to reduce nitrogen on the better part by another 50%. So we grew a 3-bale cotton with just 30 pounds of nitrogen, in season 30 pounds of nitrogen, where Dr. Wright had been preaching a 60-pound nitrogen. And on the other side, with 45 pounds of nitrogen. So this year, for the 4 hours project, the first step that I did, since I took over the project, the first step that I did, I marked using various each and every farm where we are going. And so we are collecting soil samples and tissue samples from all these different zones under a same pivot.
I have a question about the slow release fertilizer.
Yes, sir.
What happens to the polymer? Does that get into the water system afterwards?
Well, good question. My understanding, first of all, this, just for everybody's knowledge, the CRF is called controlled release fertilizer, and that's a different technology than a slow release fertilizer. And I just wanted to clarify, because as you said, slow release, yes, there are slow release fertilizers, but CRF is a different technology. It's called controlled release, because the slow release fertilizers are moisture-based, irrigation-based. So more water you apply, more of the fertilizer will be released. Controlled release, no, it's temperature-based. The higher temperature, more release. To answer your question about the polymer, my understanding, and I might get back to you on it, because I talked once with the director of research, who happens to be my old friend, and we were together at University of Georgia, and he is now the director of research with Harrell's Fertilizer, and Harrell's is one of the prominent players with developing CRF. It's a biodegradable polymer, so it degrades in the soil over time. Now, to be honest with you, I don't know if once it's degraded in the soil, what happens if the polymer components move down the profile. I don't have that information. I'll talk to him, and we'll get back to Phyllis so that she can relay that information to you all.
Thank you for your talk. I agree with Phyllis. It was fantastic and interesting. I'm interested in who is interested in your work and supports it. For instance, our Congresswoman is the only representative from Florida on the House Agricultural Committee. Does she have a degree of interest or a degree of help in what you're doing, that sort of thing, from the federal level?
Well, there has been a lot of interest from our Florida legislatures, and we invite Florida legislators whenever, if ever possible for us, on different events, and we showcase our research projects to them. And but the particular, the representative that you mentioned, I don't think that I have personally met her, but yes, I've met several of Florida state legislatures. Or, for example, met the DEP secretary who answers directly to the governor. So he stepped, Mr. Sean Hamilton, he came last year and he wanted to have a look at all the projects that we are conducting at NFREC Swanee Valley. So all in all, to answer your question, there are several legislatures that come and have a look at the work that we do and appreciate the kind of efforts we put in.
I just heard this morning on the way over here about Kat Kamek, our local U.S. House representative, was meeting with, in fact, the whole House Agricultural Committee was meeting in Florida, but I've forgotten who they were meeting with. But this is interesting to me that I would hope that they do understand your work, because this can go all over the country, this kind of scientific approach. And I would suppose that it is being applied in other places, but not being an agricultural person, I don't know. But thank you very much for the introduction to what you're doing, and congratulations on your work. Thank you very much for coming. You have a question, Bob? Sudeep? Oh. What? And this was amazing information. It's encouraging to know that there are ways to use less chemicals, rotate crops to get better yields and less pollution. Way to go. Yes. I second that emotion. Thank you all very much. Have a great day. Bye-bye.
Thank you all for inviting me, and I enjoyed it a lot. Thank you.